Welcome, class. Today we're going to be starting section 12.1. It is going to be assigned today, Monday, April 27. It's due this coming Friday, May 1. Okay. Chapter 12 is comparing multiple proportions. Section 12.1 will be a single comparisons crossed. Section 12.2 will be a two-way table. It's important to keep those straight. I'll try to emphasize that even more when we get to section 2 because it'll hopefully make a little more sense at that point. But one of the main things to catch right now is that we have in the past looked at a single proportion for a population. We've compared two of them, if you remember, back in chapters, I believe it was chapter 10, if I'm not mistaken. But now we're looking at three or more. Back in chapter 11, we looked at three or more means. Now we're looking at three or more proportions. I'm going to say that again to make sure you keep them straight. Back in chapter 11, we had three or more means. This chapter, section 12.1, three or more proportions. These next properties are going to look familiar because you've had them before. This is a multinomial experiment. We have n identical trials. So if I'm comparing proportions for Ford, Chevy, Chrysler, there would be a number of people that we would poll, and that would be in reference n. K possible outcomes. If I'm comparing Ford, Chevy, Chrysler, K would be 3. If I'm comparing Ford, Chevy, Chrysler, and Honda, K would be 4. Those are called classes or categories or excels. K must be bigger than 2. That's again because, back to our previous slide, we're comparing 3 or more. So these number of categories must be greater than 2. The probabilities of K remain constant from trial to trial. It's not like something happened when I'm polling 80 people after 38 of them have given me their opinion. I don't change things. I don't close down a factory or something in their city. So the probability remains the same from trial to trial. They're independent. Joe doesn't tell Bob what he voted or how he voted. Mary doesn't tell Deb how she should vote. The trials are independent. The variables are what we call cell counts. And this will make a little more sense as we get into an example. Okay, let's take an example here first. Suppose we know from past study done in Cleveland, Ohio, 4 brands of microwaves control the majority of the market. And the breakdown, this is in Cleveland now, for those brands is this. In Cleveland, brand 1 gets 20% of the market, brand 2 gets 35%, brand 3, 30%, and so on. We wish to perform an experiment to estimate the breakdown of brands used in Milwaukee. These first percentages were the proportions for Cleveland. I want to know, how does Milwaukee compare to Cleveland? So we take a random sample of 400 people in Milwaukee and found the following results. Of these 400 people, 102 said they prefer brand 1. 121 people said they prefer brand 2. 120 out of the 400 prefer brand 3 and 57 brand 4. The real key that we're looking at is the following. Is this 102 out of 400? Is that relatively close to Cleveland's brand 1, which was 20% of the market? Is this 121 out of 400? Is that relatively close to 35%? Or is it significantly different? Brand 3, 120 out of 400, is that close to the 30%? Or is that evidence that is statistically significant that it's a change? First thing, let's identify the parts. What we mean by that are these parts up in the previous slide, okay? Identifying the parts, 400 trials, they're identical. It's right here, it came from the 400 people that we looked at Milwaukee. There were 4 possible outcomes. They were brand 1, brand 2, brand 3, and brand 4. The probabilities of each outcome remain the same from trial to trial. It's not like we shut down the factory of brand 3 in Milwaukee halfway through. Nothing has changed throughout our questioning of the 400 people. Trials are independent, like I talked about. Here are the numbers. Now, I'm going to start by looking at 2 possible ways we can set up a null and alternative. Only one of them fits here. This particular example was Milwaukee being compared to Cleveland. Milwaukee being compared to Cleveland. So what we do is this. In step 1, our null, we start off assuming that brand 1 is going to get 20%. So we start off saying the proportion for brand 1 is 20%. We start off saying the proportion for brand 2 is 35%. Proportion for brand 3 was 30%. And that's because I'm comparing it back to Cleveland. I'm comparing Milwaukee to Cleveland. Milwaukee compared to Cleveland. Our alternative is always the same. At least one of the proportions, that's these 4, at least one of them, does not equal the hypothesized value. 99% of the time, if one of them doesn't, there's a second or a third that doesn't as well. But very occasionally, because of rounding issues, it could be just one. Now, up here, these were Milwaukee compared to Cleveland. That's because that's what the problem was asking me to determine. But what if we didn't have Cleveland up here? What would be the null alternative if I wish to just test Milwaukee by itself? That's different than Milwaukee compared to Cleveland. Compared to Cleveland means we started with Cleveland's proportions. Milwaukee by itself means I start off assuming all of these are equal. Because there's 4 of them, that means I would start off assuming all of them get their share of the market, 25%. If there were 5 of them, all of these would be equal to 20%. If there were 3 of them, all of these would be equal to 33 1/3%. I could write it, my null, like this, or I could write them all equal to 0.25, like this. Either here or here would work for your null. Notice though, these are the same when I'm comparing Milwaukee by itself. If I'm comparing it to some historical thing, in this case Cleveland, I use the historical ones up there. Again, the alternative is always the same. At least one of the proportions does not equal the hypothesized value. Okay, so those are different ways that we set up null and alternative, null and alternative. Some other details that I need to cover when I'm doing hypothesis testing for a one-way table. Right now, that doesn't make a lot of sense to you, one-way table. But what that means is I'm going basically one variable going across. In this case, it was microwaves. Just one set of data going horizontally. That'll make more sense when we get to chapter 12, section 2. But one-way table is today. Try to keep that straight from section 2, which we'll cover in the next lesson. one direction only. I'll cover that again. We have a new statistic. It's called chi-squared. Chi like in kite. I know it looks like an x squared, but that's a Greek letter chi. Chi-squared is the statistic. It allows comparison between observed distribution counts and expected distribution counts across K classes, brand 1, brand 2, brand 3, brand 4, Ford, Chevy, Chrysler, etc. The expected distribution is labeled E n sub k. That would be the expected number I would expect to get in brand K. It's going to be the total number that I polled times their expected proportion. I'll be using this formula to get expected counts. N is the total number of trials. P is the hypothesized probability. A hypothesized probability would be like in Cleveland, 0.2 or 0.35 or 0.3, etc. Here's the formula. And we are going to be expecting you to use this formula. Listen carefully now. Why am I having you use the formula? It is not to give you busy work. It really isn't. I could give you the chi-squared amount every time. But I'm asking you to use the formula because I think it will help you understand what we're measuring in chi-squared. I'm going to say that again. I'm asking you, forcing you to go through the formula because I'm hoping that when you use the formula, it will help you understand exactly what chi-squared is measuring, okay? That's the reason for making you do that busy work. The rejection region is determined by a chi-squared distribution. It has degrees of freedom, the number of classes minus 1. Ford, Chevy, Chrysler would be 3 minus 1. Brand 1, brand 2, brand 3, brand 4 would be 4 minus 1. And the desired alpha found on page 648. So if you go to page 648 in your textbook, you're going to see this kind of chart. Our alpha level, we have only these 5. Our degrees of freedom is just one column. So if I got 4 brands of microwave, I go with 4 minus 1, 3 degrees of freedom for whatever alpha level is given. I'll show that chart again when we go to a specific problem. The chi-squared is one direction only. It's because it's not a symmetric distribution. It looks like this. It is skewed right. Our rejection region is always on one side only, rejection region, which is why for my rejection region, it will always be chi-squared greater than some number because it's on the right tail. Chi-squared greater than some number. The some number will be found out of this chi-squared chart. Few more details yet. This is more if you're running this someday for your thesis or something, some conditions that are required for a valid chi-square test. Multinomial experiment, that means 3 or more proportions. Sample size is large. We've seen this before. The expected count, this has to do with like n times p greater than or equal to 5. Well, now it's the expected count is at least 5. So now we're dealing with this, greater than or equal to 5. I'll emphasize that in just a moment. That's for every cell. That's our expected count. Very similar to what we had before. This is now kind of a repeat. Hypothesis test for a one-way, that's one horizontal table. The null is often formulated as no preference. That would be if I'm not comparing it to something historical or Cleveland. I set them all equal, If there's 5 of them, it's 1 over 5 or 20%. If there's 4 of them, it's 1 over 4, 25%. If there's only 3 of them, it would be 1 over 3 or 33%, etc. But it can be formulated with non-equivalent probabilities. Remember, if I had it compared to Cleveland, they all had their own. They were non-equivalent. The alternate hypothesis, again, at least one of the multinomial probabilities does not equal the hypothesized value. Okay, well, let's go back to that example and once and try it. Okay. This is the previous problem. I put it down in a horizontal row. Notice when we went to Milwaukee, we polled 400 people. 102 people in Milwaukee said they wanted brand 1. So I put 102 for brand 1. 121 people out of the 400 chose brand 2. So I put 121 under brand 2. Brand 3, brand 4. Well, what did we expect out of these 400 people? Well, we expected, if we're comparing it to Cleveland, we expected brand 1 to get 20%. Well, what would 20% of 400 have been? 0.2 times 400. We expected to get 80. That's why I put 80 in red here. This is what I expected if it was going to be similar to Cleveland. What I got was 102 instead for Milwaukee. What did I expect in brand 2? Well, I expected, same as Cleveland, I expected 35%. Well, 35%, 0.35 times 400, I expected to get 140. That's why I put that in red. These red counts are what I expected. That's because that's what happened in Cleveland, and I'm comparing now Milwaukee. But in Milwaukee, I got 121. What did I expect in brand 3? I expected 30% of 400, which was 120. And guess what? I got 120 exact. Brand 4, I expected 15%. 15% of 400 would have been 60. Well, do you see that these two, what I expected was pretty close. These two, not so much, especially this one. Well, actually, both of them about the same. This was 22 off. This was 19 off. The question is that close enough within reasonable variance, or are these two differences, especially when you look at both of them, is that enough evidence to indicate that Milwaukee is not the same as Cleveland? That's really the heart of my test. Test the preferences against Cleveland at an alpha to see if the preferences are different from one city to the other. Well, here we go. Step number 1. My null, because I'm comparing it to Cleveland, I use Cleveland's percentage, 20%, 35 for 2, 30 for 3, 15 for 4. Our alternative always the same. At least one of the proportions does not equal their hypothesized value. My alpha level was given in the problem. Now, normally we say something here like n equals 48. I use a z-stat. Or I might have some other statistic comparing multiple means. I used an F statistic. Well, because I'm comparing multi-categorical data, that's multiple proportions, but we use the phrase comparing multi-categorical data, I tell my audience I'm using chi-squared statistic. Now I need to find the rejection region. What's in blue here would not be needed, but I do need this rejection region. Where did it come from? Where did that number come from? I go to my chi-squared chart. I have 1, 2, 3, 4 k divisions, so k minus 1 My degrees of freedom would be 1, 2, 3, 4 minus 1 or 3. So here's my chart. Degrees of freedom was 4 divisions minus 1, 3. We had an alpha level of 0.05. This 7.815 is my line in the sand. It's my rejection region. 7.814. I rounded it off here on the chart to 5. That rejection region, of course, would be needed. All right. Now let's take a look at this calculation of chi-squared. What am I doing here? And this is again why I want you to calculate these numbers out. I want you to get a sense of what does chi-squared measure. I'm not just trying to make you do busy work. I'm trying to get you a sense of the fact that these were 22 apart. Is that statistically significant, or is it within reasonable variance? This one was 19 apart. Is that statistically significant, or is it within reasonable variance? These ones we're going to definitely assume early on, these are within reasonable variance. Well, what do? I take 102 minus 80, 102 minus 80, that gives me the difference of 22. We square all those differences to make sure that they're positive. Otherwise, we could end up with some negatives, and that would cancel each other out. So we divide that by what we expected. Because if I'm 22 off here, and I expected 80, that's almost a fourth off. If I'm 22 off and I expected 17 million, 22 is not far off at all. That's why we got to divide by the expected count to give it a relative size. I divided this one by its expected count. Here the expected count was 120, here the expected count. Well, notice these first two give me fairly significant amount, 6.05 from that comparison. This one, not as much. It was 19 off, but because I expected more, 140 versus 80, didn't generate as big an amount. Here, when I was 22 off and I expected 80, that's a pretty big miss. That's why it generated a fairly significant amount, 6.05. Here I didn't generate any, here very little, 0.15. Well, we sum them all up and I get 8.7. Notice that is in my rejection region. The rejection region was anything over 7.8, I had 8.7. It is over that, it's rejected. So my conclusion, I've got sufficient evidence to reject the null, that they're going to be these proportions. And I now conclude there is a preference of brands of microwaves in Milwaukee. It's different than the preference that was in Cleveland. That's what my test shows. Don't be afraid to back this up and go through it a second time, maybe even a third time. Hit the pause, reverse it back. Do it 2 or 3 times till this makes sense. On the last test, most of you did outstanding. I think there were 35 A's out of 64. And I want to compliment you on that, okay? So for those of you that did pretty well in the last exam, please do not listen to the next 2 minutes. But for a few of you that really bombed the hypothesis test, there were 5 or 6 of you that just seemed to struggle. Listen carefully to what I'm about to say. This test is the entire answer. The answer is not just the conclusion. This is an argument. You need all of these parts. The only exception would be the blue here. You wouldn't need that. But you need all the other parts. They need to have a sequence of order, which is why we number them. So if you leave off these numbers, the problem is worth about 15 points. Leave off the numbers, -2. You blow this part up here, -3. You leave out a rejection region right there. Leave that out, -2. You mess up this calculation, -3. You mess up the conclusion, -4. It's the entirety. Notice I've numbered 1, 2, 3, 4. Some of you didn't number these. You leave off those numbers, I'm going to deduct. -2 it was last time. On the final, it will be much worse. I can't emphasize enough. All of this needs to be on your answer, not in 2 or 3 different locations, one spot. It's an argument. It is a way we persuade an audience. You can't persuade an audience if you just say something at the end. That doesn't do it. Okay, that's as nice as I can say it. But notice, I model this every time. This is about the 35th time since we started chapter 8 that I've modeled steps 1, 2, 3, and 4. That's because I want you to see that every time. You miss any of those parts, deduction, okay? Sorry for that negative. It's just been tough for some people, okay? Here's an example from a computer printout, okay? I have 3 categories, none, standard, merit. I'm expecting 60 in the none category. I'm expecting 390 for the standard, 150 in there. There's a total of 600 people that I'm going to be testing. What did I actually get? Got 42 in that category. Okay. If I were to make this out on a table, it would have looked like this. None. I actually got 42. Standard. I actually got 365. And merit, I got 193. What did I expect? I expected to get 60 in that category. I'm going to put that in red and in parentheses just to indicate that's what I expected. I expected 390 in the standard. And I expected 150. This is a one-way table going horizontal. It's not like a 2x3 contingency table where I have 2 different variables. Look at that in the next section. One-way table. It's important to keep that straight. You didn't need to copy this down, but I just wanted you to see how it compared to the previous problem. Okay, I'm testing this against what I expected. So I expected something different. I didn't expect that they would all get 33%. I expected the none to get 10%. Where did that 60 come from? Well, 10% times the total, 600, is where the 60 came from. I expected standard to get 65%. 65 times 600 is where the 390 came from. Okay? Well, here goes our test. We start off with our null. What we expected, they were different. Alternative, at least one proportion difference from the proposed plan. Number 2, I needed my comparing multi-categorical data, chi-squared. I needed my alpha. I needed my rejection region. Okay, rejection region is right here. Where did that come from? Well, that came from k minus 1. There were k, 1, 2, 3 categories. K was 3, minus 1 is 2. Alpha at 0.05. So here it is, degrees of freedom, alpha at 0.05. There's my rejection read, my line in the sand, 5.99. That's why I put that right there. This time, they gave us the chi-squared statistic. You would not have to calculate it out. 19.3, that's a huge number. We didn't just barely go over our line in the sand of 5.9. We blew it out of the water. Well, what happens here? They could give you the p-value, negative 0.05. That means that this decimal would have been moved over 3, 4, 5. That's a really small p-value. That's also like saying you blew it out of the water. this number was way past our line in the sand. This is so much less than our alpha. We definitely now have sufficient information. We can conclude the proportions are no longer the same. All right. This is an example of a computer printout that we put into all of our steps on the hypothesis test. Okay, we'll look at a few more of these yet as well. But now, before we do, we'd also like to look at a confidence interval formula. Confidence interval. This is my proportion that I observed. I'm going to put that down as observed proportion. On the previous example, that would have been 42 out of 600 for the none category. My observed for the standard would have been 365 out of 600. I wanted to show you one more of those. This observed proportion, back in this one, the observed proportion was this, 102 out of, in this case, the 400. So I would have taken 102 divided by 400. That would have been the proportion for brand 1. 121 out of 400 would have been a proportion for brand 2. Each brand would have gotten its own confidence interval. This is a Z formula. Oh, and by the way, don't think I've mentioned this yet. I keep losing my spot. What is this expected count greater than 5? That means all of these expected numbers in each cell had to be 5 or more. Obviously, the problems that we get in our book are going to do that. But if you were running some test for a thesis, you'd have to double check to make sure all of these expected numbers in red were 5 or more. Now, the observed proportion is p hat. This is my expected proportion. And of course, that would be its complement. So what did I mean by that? Well, back up here, I expected brand 1 to get 20%. So I would have had 20%, 0.2 and 0.8. I expected brand 2 to get 35. I would have had 0.35, 0.65. If I was not comparing it to some historical previous set of amounts, if I had 4 categories, it would be 0.25 and 0.75, 0.25 being 1/4. If I had 5 categories, it would have been 0.2 or a fifth. This would have been 0.8. It's my expected proportion. So again, this needs to be copied down as your confidence interval. We'll take an example of that here in just a moment. We're going to run one more test though first. Here's our next problem. Suppose I wish to determine if there's a preference toward any one of 5 different meal choices at the calf. So I've got K to be 5, choice 1, choice 2, 3, 4, 5. I'm going to pull 150, N is 150 here now. Find out their choices. Here's what happened. Choice 1, 28 people out of the 150 chose that meal choice. 35 chose, out of 150 chose 2, 33 out of 150 chose 3, etc. Run the test to determine if I have sufficient evidence to indicate the students prefer one of the choices over another. Alpha 10%, kind of low. And then we're going to do a 90% confidence interval. Okay, well, here we go. with our test. These numbers I've put right here in black. We got 28 people out of the 150 to choose choice 1. But I'm not comparing it to last year's preference. I'm not comparing it to Morningside's preference. I'm comparing it just at Northwestern. Because I'm comparing it at Northwestern, I would expect the proportion, or 1, 2, 3, 4, 5, I would expect it would be 1 out of 5 or 0.2. I would expect that they're all even. Well, 0.2 out of 150, 20% of 150 is 30. I would have expected every choice to be 30, which is why I put 30 in red, all of them the same this time, because I'm starting off with the assumption there's no preference. That's crucial that you recognize this time all of these were the same, where previously we had different numbers depending on the problem. If you remember, having very good luck relocating. If you remember previously, we had 80, 140, 120, 60. It's because I was using the proportions for Cleveland. There is no Cleveland here. That's why I start off assuming they're all the same. Those are my expected counts. So here we go, step number 1. The null. I start off saying they're all equal. They're all equal to 20%. That's because I had 5, 1, 2, 3, 4, 5. 1/5 is 20%. My alternative, at least one of the proportions does not equal its hypothesized value. Fairly large alpha amount. Well, let's get our rejection region a minute. Okay, there were 5 categories, so K minus 1, 5 minus 1 is 4 degrees of freedom, alpha level at 10. 4 degrees of freedom, alpha level at 10 is 7.779. That's why my rejection region is chi-squared is greater than that number, 7.779. You don't need this in blue. I was just trying to show where it came from. You do need comparing multi-categorical data. Tell your audience I'm using the chi-squared statistic. Okay, now let's go back to here. We expected 30, we got 28. So I take the difference, square it to make sure it's positive, divided by its relative size of what I expected. 35 minus 30, positive already, but I square it to be sure. These 30 should be underneath all of these. Computer printout, move that over. Notice we were pretty close in all of them. Here I was 2 off, 5 off, 3 off, 5 off, 1 off. When we generate all of those numbers together, we only end up with 2. It's not bigger than 7. It's not over our line in the sand. It's insufficient evidence. These are within reasonable variances. So I have insufficient evidence to reject my null. I thus continue to assume there's no preference for these 5 choices. No preference. Okay? Again, maybe pause it, rewind it, see if you could write these out. Again, for those few, notice I numbered all the steps. I have all the details. The entire argument from 1 to 4 is needed in this sequence in one location for you to have a correct answer. If you mess up this, if I put 0.25 here, that would be minus 3. Okay? If I mess up one of these points, likely minus 2. If I miss the rejection region, minus 2. If I miss step 3, minus 3 or 4. If I make a wrong conclusion, minus 4 probably. All of the steps have to work together because they are an entire argument. Okay? Just this will get you minus 12 out of 15 points. All right? Because that means nothing without the entire argument with it. Okay? Again, Most of you are just nailing these. For the final, most of you, the hypothesis test will be the easy part. Now, if you remember, this is that same paper, I'm sorry. If you remember the original, said to form a 90% confidence interval for just choices 1 and 2. You can do these for all 5, but we're going to do just 1 and 2. Okay? So here we go with that confidence interval for just choices 1 and 2. Our formula, which we had on a previous slide, for the confidence interval, this would be the proportion sub I. That's the observed proportion. I meaning it could be 1, the observed proportion for proportion 1. I could have been 2 here. I could be 3, could be 4, etc. For 1, this would be the observed proportion for 1. It would be 28 out of 150. So observed proportion for 1, 28 out of 150. The observed proportion for 2 would be 35 out of 150. And you would get those decimals. Remember, this was the observed. This is what we expected. We expected all the proportions to be the same. So my expected proportion, because they're all the same, we're setting them all equal. There's 5 of them, that's 1/5, or 0.2. This would be 0.2, this would be 0.8, n would be the 150. So that's where we're getting all these numbers from. Okay? Proportion number 1, 0.187 is 28 divided by 150. This is our Z formula for 90% confidence interval. That takes us back, but you've done that a million times. Notice I didn't use 0.187 here. I used what we expected. The expected proportion, 0.2, 0.8. This is what I ended up getting. Now, notice for confidence interval for 2, this is the observed, 35 over 160. That was 0.23, different than 1. Same, same. Okay? This is what I ended up for my confidence interval. Well, what does that interval mean again? It means I would be 90% sure that the true proportion of students that would choose number 1 as their favorite is somewhere between 13 and 24%, between 13% and 24%. I would be 90% confident that the true proportion of all the students that voted for choice 2 as their favorite is somewhere between 18% and 28.7%. Okay? Now, I would like you to notice here. Do you see that this first interval, 13% to 24, do you see that it includes the 20%? It includes what we expected it to be. Because 20% is included in there, that is why, this is our previous test, it's why we had insufficient evidence. It was within reasonable variance, 28 when we expected 30. Pretty close. This included our 20%, what we expected. Same thing here. It was a little different interval, but it still included 20%. That's why we had insufficient evidence to indicate that there's a difference in preference. Notice those intervals also overlap. 18 is lower than 24. 24 is higher than 18. These intervals overlap. One is here, the other one includes an overlapped portion. That again means you're not sure which one is greater. That's why we continue to assume they're all at 20%. What should be true about all 5 intervals? If I ran these 2 formulas for 3, 4, and 5, all of those intervals would also include 20%. That's again why, in this example, my hypothesis said insufficient evidence. I had to continue to assume no preference. They basically supported each other's argument. Okay. Another example. This will be our last example here today. Consumer Report magazine polled 200 of its readers, that's n equal to 200, in some particular state to determine a preference of 4 car companies, Ford, Chrysler, Chevy, Toyota. Which one is their favorite? Well, these are observed counts. They observed 46 out of the 200 prefer to Ford. 76 out of the 200 prefer to Chrysler. Okay? Run the test to determine if there is a preference toward any particular car company. All right? Notice I'm not comparing it to Cleveland, or I'm not comparing it to 2018 or 2015 or last year. I'm just running it one time. So I'm going to start off assuming they're all the same. There's 1, 2, 3, 4. So I would start off assuming the proportion for Ford, P sub F, equals the proportion for Chrysler, equals the proportion for Chevy, equals the proportion for Toyota. Because there's 4 of them, that would be 1/4 or 0.25. I start off assuming all of them should get 25% of the choices, 25% of the market. Well, what is 25% of my number that I'm polling? 200? 25% of 200 is 50. 0.25 times 200 equals 50. I expected to get 50 for every one. That's my expected count. This one, pretty close, only 4 off. This one, big miss, 26 people more. And when you only expect 50, that's a big miss. 26 off if I'm expecting 5 million is not a big miss, but 26 off if I'm expecting 50, big miss. 6 off, not so big. 16, pretty significant miss, about 1/3 of what I expected. Okay, I'm going to run the test at an alpha of 5%, then we're going to have a corresponding 95%, 5% corresponding confidence interval. So here we go with our test. I recopied them down and I put the expected counts in. Basically, that's just right off of what I did right here. You have to calculate that 50. Start off by assuming they're all equal at 25%. That's because I'm not comparing it to 2015 preferences or 2017. I'm just looking to see, is there a preference? At least one of the proportions does not equal its hypothesized value. Start off, list my alpha. I'm telling my audience, again, this all is now part of my argument to convince an audience. I need all of these parts. I'm telling my audience I'm looking at an alpha of 5%. I'm telling my audience I'm comparing multi-categorical data. It's 3 or more proportions. That's why I'm using a chi-squared statistic. My rejection region. I have to find a chart back. Here's one. This one has a different marking, but I have alpha at 5 1, 2, 3, 4 minus 1 would be 3. So I would go 3 here. I come off of 3 over to the 5. That's where I got my rejection region, 7.815, 7.815. I rounded it off. That's my rejection region. Here I go with my calculations now. And again, this isn't busy work, okay? This is trying to help you understand what you're measuring. You're measuring how far off was 46 compared to what we expected, 50. If I compared it to 5 million, that wouldn't be off much, 4 in 5 million. But 4 in 50, that's a little bit more. Here I missed it by quite a ways, 26 out of 50. It's almost half of 50, a little bit more than half. That's a big miss. That one's going to calculate a large number. That's going to be a significant part in getting to 19. Here I missed by only 6, not so much. Here I missed by 16, a little bit more. Well, when you calculate all of those, this would be, of course, 4 squared is 16 out of 50. This would be 26 squared over 50. 6 squared over 50. 16 squared over 50. You get 19. 19 is in the rejection region. It went over our line in the sand. Visually, my line in the sand for my rejection region was 7.8. What did we get? We got 19. We're way over here someplace. I went over that line in the sand. It was greater than my rejection region. All of this is in your rejection region. This one right here generated a large amount. This one, pretty large amount as well. But those two especially made this number big enough to get over into our rejection region. That's what I'm hoping you understand when you calculate the chi-square. This 46 came from right here, minus 50, 76 minus 50, 44 minus 50, 34 minus 50. I have now sufficient evidence. So my conclusion, I have sufficient evidence to reject our null. I now conclude there is a preference in the car company chosen by the public. Okay, let's take a look at our confidence intervals. They should support this conclusion. Again, though, before I do that, again, most of you are awesome at this, so please close your ears if you are. But for the few of you that messed up on this, I don't need this red drawing, but I need everything else, including these 1, 2, 3, 4. You leave these off, 2 points off, it'll be 3 or 4 points off on your final. It's because these are organized in a sequence. I need every part here. Any part missing or any part incorrect, deduction out of 15 or 20 points or whatever the problem is worth. Okay? The whole thing is an argument. Just that answer means squat. Okay? The whole thing is your argument. Okay, the rest of you can now open your ears. Won't be too negative. This right here is our confidence interval formula. What is P sub I? Well, that would be, in this case, the 46 out of the total number that were selected. And I lost my previous page. It's right here. We had 200. So in this particular experiment, there were 200. So we would have taken 46 divided by 200 to get the proportion for 1. This would have been the 0.25. It's what we expected. This would be 0.75. So it would look like that. Apparently, this was for the Chrysler now. Be careful here, it's Chrysler. 76 divided by 200 is 0.38. My z-score, 1.96, you've seen that before. 0.25, its complement gives us this interval. What does that mean? I'm 95% sure that the true proportion of people that will choose a Chrysler is somewhere between 32% and 44%. Toyota, I'm doing next. It was the low one. 34 divided by 200 gives you 17. 34 divided by the number we pulled. This is, again, right off of our null hypothesis. I am 95% sure that the true percentage that will vote for Toyota is somewhere between 11 and 23%. Would you agree these two do not overlap? This one is far to the right of that one. All of it is to the right of all of this one. There's no overlap. That means I'm 95% sure Chrysler has a bigger share of the market, which would be obvious here for a couple of reasons. Chrysler had the largest share, Toyota had the smallest share and are observed. That's why we had sufficient evidence to reject. The real question would be now, if you ran it for the other ones, would there be enough evidence to indicate that this one is less than Chrysler? Or is this one less than Chrysler? Or is Toyota less than Ford? We would have to run all of those. Notice neither one of these intervals included 0.25, which is what we thought they would be. That's why we had sufficient evidence, okay? These intervals do not overlap. That's going to be all we have for today. So we're assigning here again, section 12.1. You guys are doing an awesome job of these hypotheses. Keep up the good work as a whole. That's why your tests were so good last time, a whole lot of A's. Have a good rest of your day.